Let's delve into the world of NP-complete problems. We'll explore the Cook-Levin theorem and the concept of NP-completeness. We will cover complexity theory to understand computational difficulty and problem classification. Also, polynomial reductions to transform one problem into another efficiently. Let us review the classes P and NP. P stands for polynomial time, which means these problems are solvable in polynomial time, that is, order of n to the power of k, where n is the input size and k is a constant. NP, on the other hand, stands for non-deterministic polynomial time. These are problems where a solution can be verified in polynomial time. What exactly does it mean for a problem to be NP-complete? A problem is NP-complete if it meets two key conditions. First, the problem must be in NP, meaning it is verifiable in polynomial time. Second, every problem in NP must be reducible to it in polynomial time. The Cook-Levin theorem is a cornerstone of complexity theory. It states that SAT, or Boolean Satisfiability, is NP-complete. This was the first problem proven to be NP-complete, and it established the foundation for all other NP-completeness proofs. Let's define the SAT problem more formally. Boolean satisfiability asks, given a Boolean formula, does there exist an assignment of variables that makes the formula true? For example, consider the formula x1 or not x2, and x2 or x3. The challenge is to find values for x1, x2, and x3 that satisfy this formula. Polynomial reductions are a technique used to show that if you can solve problem B efficiently, then you can also solve problem A efficiently. You transform instances of problem A into instances of problem B using a function, denoted as f of x. The key property here is if B can be solved efficiently, then A can also be solved efficiently. Here are some classic NP-complete problems. 3 coloring. Can you color the vertices of a graph with 3 colors such that no adjacent vertices share the same color? Knapsack. Can you select items with maximum value while staying within a weight constraint? Hamiltonian path. Can you find a path that visits each vertex exactly once in a graph? Clique. Can you find a subset of vertices where every pair is connected by an edge? The implications of NP-completeness are significant. The big question is, if any NP-complete problem has a polynomial solution, then P equals NP. The key takeaway is that NP-complete problems represent the hardest problems in NP. Solving one efficiently would mean solving them all efficiently. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.